again in this advanced conduction series. So in the previous class, in the previous lecture, we were discussing about the thermal network, and we showed the analogy of thermal network with the electrical network. And I also showed you that I mean, in the lecture there was some note, and that note was showing that I was actually taking the geometric mean concept wrong. Okay, so and I have already showed in that lecture that what should be the actual formula for the geometric mean, and that will solve the issue. Okay, so in this lecture we will be starting something more that most probably you have not dealt with in your B.Tech, okay, in the traditional heat transfer course that we all have done during our bachelor's. Okay, and some of you may have done that. Okay, so now just before that I will put another concept with you, that is, okay, so first let me put the lecture number. Today is lecture 9, right? Something is flying around me. It is a small bug. Okay, so just let me see the lecture number. I think it is lecture 9, right? No, it is 10. I always forget the lecture number. That is an issue. So this is lecture 10, and let us start with some concept, that is, if let us say that we have a sphere. Okay, so every time I take a cylinder only, so this time I have a sphere. So this is a sphere, and this sphere is having an uniform heat generation rate, that is Q triple dot. Okay, so now, and also the ambient is having heat transfer coefficient H and temperature T ambient, that is given. Okay, so you have to actually find, okay, if this is my r coordinate, the radial coordinate, that is r. Okay, so then you have to find this T at r equals to r. This is so disturbing. Okay, so T at r equals to r, where this r is a radius of this sphere. Okay, this is r, and minus T at r equals to 0. So the surface temperature minus the center temperature. Okay, so how can you find this? So you see, first of all, if I take in r distance, at r distance, if I take, so this has become an ellipse. And this is not converting to a sphere. New problems. Okay, that is fine. Now it is okay. So at r distance we are taking some elemental sphere like this and this. Okay, so now, and this thickness is what we call dr, right? And so if Q triple dot is the volumetric heat generation rate, that is the heat generation rate per unit volume, you tell me that within this amount of volume, how much is the heat generation rate. Okay, so that will be this volume. Okay, right, that will be this volume, and this volume will be what, 4/3 pi small r cube into Q triple dot, that is heat generation rate within radius r, right? Okay. So now you tell me that if I have to maintain the steady state, okay, so steady state means what? Steady state means that nothing will change with time, that is the temperature will not change with time. So if I am saying that the temperature will not change with time, that means from the system, if any heat is generated within the system, then that heat must come out from the system. Otherwise, if there is any accumulation of heat, there will be some rise of temperature. Conversely, if there is a sink, if there is a heat sink within the system, then there will be a drop of temperature. So no amount of heat can disappear from the system, and no appear of extra heat can accumulate within the system. So here I have some heat generation. So if the system has to remain in steady state, the heat that is generated, that has to come out from the system, right? That means from this small volume within the radius r. So if I am saying that this is the amount of heat that is coming out at the radius small r. So that will be what? That will be minus k del T del r into A of r. And what is this A? This A is the surface area of the smaller sphere of radius small r, right? And I can write this as dt dr, considering that only one dimensional heat transfer in r direction, right? And this must be equal to the rate at which the heat is generated, right? So now I have a governing equation for temperature. So this AR is what? AR is 4 pi r square, and this is 4/3 pi small r cube into q triple dot. Now some things will be cancelled out, so this 1 r will be cancelled out, pi and pi, 4 and 4 will be cancelled out. So the things which remain are this is equal to r small r q triple dot by 3, right? Okay, so here these things are constant, q triple dot and k. So that means I can do this integration. So this is from t equal to 0 from t equal to capital R, because I want to find the difference between them. Now you see, you can put here any r value. Here instead of capital R, you can put any r value, anyone, okay, anything you can put, and you can get the you can get that temperature with respect to the center temperature, right? So that will be equal to what? That will be equal to q triple dot by 3, obviously minus, and k will be, and this will be 1 by k, right? And this will be r dr from 0 to r, right? So if you take the temperature at any other radius, then this r will also be changed, right? Now I think the algebra is correct here. All of you must be very careful about the algebraic steps, and if you find any mistake, then you must write that in the comments, so that other students who are having the same doubt can get clarified through that comment. And I also, if I can see those comments that there are some mistakes, some algebraic or some or maybe some other mistakes, then I can also correct that in the upcoming videos. So here that will be Tr minus T0 equal to minus q triple dot 3k into capital R square by 2, right? Okay, So now you see, so this is the temperature difference, right? Okay, fine. So that is finally minus q triple dot by 6k into r square. Okay. So you see that here there is a negative sign, and can you tell me that if there is a heat generation, that is this value of this q triple prime is positive, then which temperature should be more, center temperature or surface temperature? That is the center temperature, right? So that means this equation is mathematically correct, because if I invert this equation, then this becomes, now this becomes positive, and this directly is telling me that center temperature is greater than surface temperature. Okay, another thing that I have also given you this heat transfer coefficient and T ambient. So what I have told, that the heat that is generated in the sphere, that should come out through the convection in the air, right, or in the ambient fluid. So here I can also write, that is the heat that is generated in the sphere, okay, that is the total 4/3 pi capital R cube into q triple prime, that is equal to H into T of R, T at R, that is surface temperature, in minus TA into A of S, that is the total surface area, right? So if I write the equation again, so Q, that is heat transfer from the surface. Okay, so many times we actually forget that we can apply these simple things. Okay, that is, if I give the same problem, and if I ask you that what is the heat flux from the surface, then you might think any rocket science, right? But that will be just heat flux means what? That is the heat transfer rate per unit area, and heat transfer rate must be the rate of heat generation, that is this. So to get the heat flux, you just have to divide this with the surface area, and that will be equal to, so if you divide with this surface area, then that will be equal to H into T at R minus T ambient. Okay, so thusly you can see, so I will just do the mathematics here. So 4 pi r cube q triple prime, and here this area will be 4 pi capital R square, that will be equal to H T at R minus T ambient, and that is, now I can cancel out this 4 pi 1 R, right? So this will become R q triple prime by 3 equal to H TR minus TA. So here you see, you have also got the difference between surface temperature and the ambient temperature in terms of the known quantities, and here you had the difference between center temperature and the surface temperature. So you can also get the difference between the center temperature and the ambient temperature, right? So these concepts are very important for GATE, and not only for GATE but for anything regarding conduction. Okay, so now your homework is to derive this same thing, that is the so if I have a slab, okay, if I have a slab like this, okay, and this is the mid plane of the slab, so this length is 2L, so this is L, this is also L, okay, and you have ambient here H and H, TA, both sides same ambient, and the heat generation rate is Q triple prime. You have to find this T at 0 minus T at L at any side, okay, and similarly if you have a cylinder like this, okay, if you have a cylinder like this, and this is the center plane, again you have to find the same thing. If you have this ambient H and TA, you have to find the difference between T at 0, T at R and T at A. The expression will be something similar to this, okay, but some numerical values will be different. This 6 will not be there for sphere and the slab, there will be some other constant. Similarly, this 3 will not be there for the slab and the cylinder, and there will be some other constants. Okay, okay, so now this is done. So now let us move one step further, that is, up till now we have only considered the steady state and also one dimensional, right? So now let us just relax one of the restriction. So now we will be taking up the case of transient, okay, transient one dimensional, okay, transient one dimensional heat transfer. Okay, in a slab. So from now onwards, please pay your attention, because even if you already knew the previous concepts that I have talked up till now, because maybe you have done that in your B.Tech or BE, I am sure that 90% of you have not gone through these concepts. I mean, you should have gone through this concept in your engineering mathematics course, but in most of the colleges, okay, engineering maths is a very neglected course, and that is why uh, most of us have already avoided this concept, okay, and I will talk about that. So firstly, let me talk about the question, and that is, this is our slab, okay, this is our slab, and here what you do is, at time t equal to 0, that is the time instant from which you have started your observation, at time t equal to 0 you have set this wall temperature as T1 and this wall temperature as T2. Both of them may be equal or both of them may be unequal, okay. So now, and all the properties are given. This is K and this length is maybe 2L, okay, this length is 2L or L, only L, okay, I am sorry, this length is only L, and this thermal conductivity, this is thermal conductivity, okay. And at t equal to 0, this was the case, and for all time, for t greater than 0, okay, I mean from the instant sorry, from the instant at which you have started your observation, from that instant you have set the temperatures of both the phases at T1 and T2, you have maintained that temperature. So for all time at t greater than 0, that is at any time after the start of observation, these two temperatures are maintained, and at t equal to 0, that is just before you have started your observation, the temperature in the block was given at Ti throughout the block, okay. That is, it is a very practical problem, that is if you have a solid slab and that was at the that was in thermal equilibrium with the ambient, so maybe the ambient was at 30 degree, and that is why the slab was also at 30 degree, right? And at some time, um, you have fixed maybe two heaters at one phase and at the another phase, and those two heaters are doing the job of maintaining the temperatures of those phases at T1 and at T2. So now your task is to find the temperature distribution. So the moment I say temperature distribution, some of you have already thought that it will be a function of x, that is the space. But now see that this will not be a function of x only, because everything is varying with time. So at t equal to 0, there was already a steady state temperature distribution, that is t equal to Ti for all x. But now the moment you have altered your boundary condition, so earlier what was the boundary condition? Boundary condition was that there is an ambient having the temperature as 30 degrees Celsius. But now the boundary condition has been changed, that is at one side I have T1, at another side I have T2, right? So that is, the boundary condition has been changed, and accordingly the solution will evolve with time. And I think this you can feel also, right? That is, if you started to heat up the body maintaining some temperature at the two phases, so it will not be heated up just in a blink of an eye, okay? So that will not be the case. It will be heated up and it will attain a steady state temperature distribution after a particular amount of time. So we have to find the temperature distribution that is a function of space as well as a function of time. Clear? Okay. So now if the problem is posed, so now let me draw the coordinate axis here. Okay. So today my camera is actually not working in a very good manner. Just let me see. Just you guys give me some time to fix just my camera. Okay, I apologize for that. Okay, so I think it is visible. So now let me solve this problem. So you can take your coordinate axis anywhere, okay, but I will take my coordinate axis now here, okay. So always you guys just remember that you have to, I mean, in any problem, the things that are in your control, like the choice of the coordinate axis, the position of the origin, so these are in your control. So you should choose the coordinate axis in such a way that the calculations are minimized, that the description of the problem, that is the mathematical description of the problem, get simplified. So you can choose the coordinate axis anywhere and in any direction, that is totally fine. And okay, so my camera is showing that unable to use flash due to high temperature. Okay, so I think I know the problem, that is it is charging, and that is why. Okay, So actually it was also a heat transfer problem. That is that is my phone was charging, and that is why it was getting heated, and because of that it was showing that the flash cannot be turned on because of high temperature. So the phone was at high temperature. Okay, so that can also be a very interesting heat transfer problem. That is, if you are an engineer and you have to design the cooling system of the phone, and you know that after this much amount of charging, the phone will be heated up to this much temperature, at which the flash can be turned off. So your job is to design an effective cooling system inside the phone so that the flash can be turned on. That is, the temperature should not go up beyond a particular value. So all these practical things are very, I mean, interesting. You can do some mathematical estimates with the tools that I am just teaching you, right? Okay, so just let us go back to our problem. Okay, just let me make sure that the video is turned on, right? So I'm sorry because today there is so much disturbance, I know. So here I was talking that you should choose your coordinate system in such a way that the uh, calculations as well as the mathematical description of the problem can be simplified as much as you can. Okay, so here as far as I see, uh, I can choose this as my x. Okay, here, and this is my origin, and obviously this is my y and this is my z. Okay, that is clear, but here this y and z are not important because it is an one dimensional heat transfer in x direction. Okay, clear, in x direction. So now you just pause the video and write the governing equation first for every problem. I mean, not only in heat transfer but also in fluid mechanics, in solid mechanics. In every problem, the basic step is to write the governing equation. Okay, so here you just pause the video and try to write the governing equation. So I hope that all of you have written the governing equation. So the governing equation will be your del 2t del x2, okay, equal to 1 by alpha del t del t, okay, del small t. So previously we were not having this term, that is the transient term, right, but now we are having that. Clear? So this is our governing equation, and what will be the boundary condition? So boundary condition is at, or I can write, for all t greater than 0. So this sign is the for all. Okay, this sign is indicating for all. So for all t at t greater than 0, I have 1, that is t at x equal to 0, that is t1, and t at x equal to L, that is t2. Correct? Okay. So again I think my camera has stopped, but this time my phone is becoming cool. So let me turn on the camera. Okay, and if this time my camera turns off, then I will not turn it on again. Okay, because it is becoming a real issue. So this is the boundary condition and this is the initial condition. Okay, so this term is new for you, It is the initial condition. So as the name suggests, it is the condition for the whole block at time t equal to 0, and that is why it is called initial condition. The condition for whole block at the initial time point from which you are starting observing the block. Okay. So the initial condition says at t equal to 0 for all x t equal to ti, t initial. Okay. I could have written this boundary condition as t x equal to 0 comma t is equal to ti, and t x equal to L, I should have written t greater than 0 at t equal to t equal to t equal t2. So and this will be t1. It is the same description, okay, in different representation. And also I could have written this one like at all x and t equal to 0 is equal to ti. So you must learn all the representation. You see here that this problem is having a second derivative in terms of the space. So we need two boundary condition for space, and here we have the two boundary condition. And you see here I have a first order derivative with respect to time, okay, and therefore I have only one boundary condition for time, okay. So the order of the derivative will say you that how many boundary conditions you will need for that derivative, I mean for that variable, okay. So because I have the second order differentiation with respect to x, that is why I need two boundary condition for x, and I have a first order derivative with respect to t, that is why I need only one boundary condition, or here we say it an initial condition for the variable t, okay. So now if you have done CFD in your bachelor course, the computational fluid dynamics, and even if you have not done, can you say that I mean what is the type of the equation? So we know that the differential equations can be classified into three types, that is parabolic, elliptic and hyperbolic, right? So this equation is elliptic in space and parabolic in time, okay. So and from the perspective of CFD, if I have parabolic in time, then that will denote some behavior like this, that if I have something at t equal to 0, I have mentioned maybe t equal to ti, then I can find all other t values after that t equal to 0, but not before the t equal to 0, okay. So in fluid mechanics also you can have these types of equation, okay, like you can have del 2u del y2 is equal to, so nu is equal to del u del t, okay. So you can have this type of equation. So here also this is parabolic in time, okay. So you cannot find any temperature value before time t equal to 0, okay. So now this was my mathematical description, and this problem also is known as my initial boundary value problem, because it is having one initial condition and two boundary condition. So this is also called an initial boundary value problem. Okay, so these terminologies you should know actually. And so now let us continue. So now you have to solve the problem, and let us see that how can we solve the problem. So before solving the problem, I will introduce another condition, that is the non-dimensionalization. So what do we mean by that and why we need that? So non-dimensionalization means that is, see, this T has an unit, maybe Kelvin. This small t is having an unit, that is maybe seconds. This x is maybe having an unit of meter, right? And this alpha is also having some unit. I have actually forgotten the unit, you can derive that. Okay, but now I will define something called theta, and that will be this T by some reference temperature. And you see that this is having the unit Kelvin, this is also the having the unit Kelvin. So all over this term is unitless, right? So this term is unitless, or it is non-dimensionalized, non-dimensional term. Okay, this is a non-dimensional term and this is a dimensional term, dimensional temperature, and this is a non-dimensional temperature theta. Similarly, I will define a variable, so let me define this with another color, the non-dimensional ones. So I define tau as some t by some t reference, some reference time scale. Okay, and I also define some x bar as x by x reference. So this t reference, this small t reference, and this x reference, all are constants. Our job is to choose this constant. Now again, you guys just recall that statement, that whatever thing is in your control, you must choose them in such a manner that will simplify your algebraic calculations. Okay, so we have to choose this t reference, this small t reference, and this x reference. Frankly speaking, that you can choose as per your choice. I mean, you can choose this anything. Okay, that will not differ the solution of the problem. The solution will come in some other format, but ultimately when you will find the dimensional solution, that will be the same. But you have to keep in mind just one fact, that is you have to simplify your calculation and the mathematical description. So let us see that how can we do that. So firstly, in terms of this t reference, small t reference, and x reference, that is in terms of this theta, tau and x bar, let us write our governing equation and the initial and boundary conditions. Okay, so the governing equation, so I will here write actually non-dimensionalized problem description. Okay, problem description, clear? So just let me copy the governing equation first. So this is my dimensional one. So this is dimensional governing equation. Okay. So here you see how can you non-dimensionalize this. So I know that my, so just put your focus on this. Theta is equal to T by T ref, where T ref is a constant. That means del T, del theta, del T is equal to del T, del T into 1 by T reference. This 1 by T reference is outside the derivative, right? Now you see that my tau is equal to small t by small t ref. Therefore, if I write d tau, that will be dt by t ref, right? In other words, I can write my dt is equal to t ref into d tau. Okay, so that means you see here I can write this del t as t ref into del tau. Okay, so my this becomes actually, okay, so let me write it like this only. Okay, that is fine, I don't need to. So from this equation, this is equal to this into t ref, right? And now if I have to change this t from tau, then I can write this by small t ref. Okay, that is I have written this t as, or this del t as del tau into t ref. Okay, because I have already proved that. You see, you are having here theta equal to t by t ref, and you are having t here, and to convert this t to theta you need to multiply just one t ref and see this t ref where in the denominator here, and here you have t. So here to convert this t into tau you have to multiply one t ref in the denominator. Okay, so it is just like t is equal to this, t is equal to theta into t ref, just like this, t is equal to theta into t ref, and here this small t is equal to tau into t ref. So now you just tell me that had I defined this theta equal to t into t ref, then without doing calculation can you tell me that what would be the change in this expression? So if theta is equal to t into t ref, that means it is equal to t by 1 by t ref, right? And here t ref was at that denominator. That is why if I have to go from t to theta, I had multiplied t ref here. But here I had, if I have theta equal to t by 1 by t ref, now I have 1 by t ref in the denominator. So to convert from t into theta, I need to multiply 1 by t ref. So had I defined this theta is equal to t into t ref, this expression would have been not into Tref but into 1 by Tref. Okay. So the trick is, the moment you define the non-dimensionalized variable, the thing that is in the denominator of the dimensionalized variable, that is the thing that you have used to non-dimensionalize your dimensionalized variable, that will be multiplied with that variable to convert it from the dimensional version to the non-dimensional version. I think you will get used to it. Okay. So you just take care of this thing that I have find this del t del small t is equal to del theta del tau into T ref by small t ref. Okay. So now let us find again what will be this del t del x. So you see, I have to go from t to theta. So then I will multiply 1 T ref here, and here I have to go from x to x bar. So now again just pause the video and just tell me that what I should multiply here. Sorry, what I should multiply here. So I think you have got the answer. The answer is, that is the, in the denominator of this x I was having this x ref. So to go from x to x bar I need to multiply with x ref. Okay. So here I need to multiply with x ref. And if you forget this trick or this thing, then you have always the option to go step by step, that is my del t del x will be equal to, so what is t here? T is equal to T ref into theta, so that will be, I can always write this as T ref into theta, that is my t, by x is what? X bar into x ref. Now you see, because this T ref and x ref, these are constants, this will come out of the derivative. Okay. But this is the short trick, and that can save your time in examination. Okay. So now you tell me, if I have to write del 2t del x2. So here again I have only one t. So from this t, if I have to go to theta, only one 2 is there. You don't just confuse yourself by saying that if I have here 2, that means I have here 2t. No, you have only one t. This is what? This is del del x of del t del x. That means you have two x coordinates here. So to go from 1t to theta, you have to multiply by t ref, but you have here 2x. So for each x bar you have to multiply one x reference, and that will be one x reference whole square. So that is the transformation for del 2t del x2. Clear? Now I have these two. So from this one and from this one I can write, that is my governing equation is now, see, del 2 theta del x bar 2, my t ref by my x square ref is equal to what? Del theta del tau into, okay, there was 1 by alpha, that is fine. Okay, by t ref by tau was small t ref, and because these are constants I can cancel these out. Now you see, now also this equation, this one is not a non-dimensionalized equation, because this term is not having any unit, but this term is having an unit. This term is having the unit of 1 by meter square. Again this term is not having any unit, but this 1 by alpha into 1 by t ref is having an unit. Okay, but now to make it non-dimensionalized, what I will do is I will multiply or I will divide by any of the coefficients of these terms. That is, I have to divide either by this term the whole equation, or I have to divide by this term the whole equation. Okay, so let me divide it by 1 by x reference square. So in other words, I will multiply both sides by 1 by x reference square. So that will be this one. So let me write it like this: del theta del tau x square reference by alpha t reference. Okay, clear? So now you see this term is a non-dimensionalized one, this term is also a non-dimensionalized one. So this must be also a non-dimensionalized number, because see, this is a non-dimensionalized number. If this is having any unit, then this must have an unit, because this has no unit. So if this has a unit of meter, so an unit of meter is the unit of this whole term, so then this should also have an unit of meter, but this is not having any unit, and that is why this term must also be non-dimensionalized number. Okay, and see, this is called actually the Fourier number. Okay, that is the alpha t by x square. This is the Fourier number. Okay, so I can write this alpha t by x square. This is the Fourier number denoted by FO. Clear? So this is my non-dimensionalized governing equation. Up till now I have not assigned any value to this x reference and t reference. Okay. So I will do that in the subsequent thing. Okay. So, but one thing, in this step you see that I can assign any value to this x reference and t reference. So why not assign some value so that this becomes 1? Okay, I want that this expression turn down to 1. Why? Because then my governing equation will just be this equation, and that is very simple in terms of its mathematical description. Okay. So if this is 1, then at least I have a correlation between T ref and X ref. Okay. See, these are totally your understanding. Okay, no one will tell you. Okay, I mean, maybe the professor in the question paper will tell you that you take this as your non-dimensionalized variable, but it may be the case that the professor will tell in the question that you non-dimensionalize the variables by your own, you take the reference variable by your own, then you have to judiciously take these kind of things. That is the what should be the value of x reference, t reference and small t reference, so that your problem gets simplified. Otherwise your problem maybe get complicated. Okay, and that you don't want, right? So until now this is my non-dimensionalized, I am writing a short governing equation, and that is my del 2 theta del x bar square is equal to del theta del tau. And here I know also this thing, that is my t reference is equal to x square reference by alpha. Clear? So now let us come to the boundary condition. Okay, so let me again just copy these boundary conditions and also the initial condition. I will copy this whole thing here. Okay. So let us come to first this equation. Okay, it is saying, or this equation. Okay, so the boundary conditions, okay, obviously non dimensionalized. So it is saying that is t at x equal to 0, t greater than 0 is equal to t1, correct? So now I have to turn this t into theta, this x into x bar, this t into tau, right? So if I turn this t into theta, then I have already defined, okay, so now you do not have to look at the definition, you know that to turn t into theta you have to multiply by 1 t ref, and if you have to multiply this sorry, if you have to turn this x into x bar, you have to multiply x ref equal to 0, and to turn this t into tau you have to multiply t ref is greater than 0, and this is a constant. Just do not say that I have to turn this into theta 1. Yes, this will turn into theta 1 into some another thing, okay, but now this is a constant. You cannot turn this t1 into theta 1 by just merely saying that this will be theta 1 into tf. That is not correct, okay, because you have not defined theta 1. This theta 1 is not defined, that is not correct, okay. This t1 is a constant proposed by the problem. So now you see, that means this theta at x bar equal to 0, because x ref is a constant, and at tau greater than 0 is equal to t by t ref, okay. And again, now the second one, that is my, the second one is at x equal to L, at t greater than 0 I have my temperature as T2. So now to turn this into theta, this into x bar, this into tau, and nothing else. Again, you do not have to turn this L into L bar or anything like that, right? So now this will be theta into t ref, right, x bar into x ref equal to L, so tau into t ref is greater than 0 is equal to T2. So that will be equal to theta at, now you see, theta at x bar equal to L by x ref. Previously for boundary condition 1 I was having 0 here, so that is why this x ref was eliminated. By now this x ref is there, okay, and my tau greater than 0 is equal to T2 by T ref, clear? So you see one thing, that this is your description of the boundary conditions, right, this one. So let me just write this in one place, okay, just let me write the initial condition also. So initial condition in non-dimensionalized, okay. So I have my t for all x, and at t equal to 0 is equal to ti. So that means I have to again turn this t into theta, this x into x bar, this t into tau, right. So that will be theta into t ref, x bar into x ref, and that Tref into tau is equal to 0 is equal to Ti. That means my theta at x bar into x ref, right, comma my tau equal to 0 is equal to what? Ti by Tref. Clear? Okay. So now you see one thing. In all this expression, what you can do to I mean simplify your problem. One thing you can see that here I have x equal to 0 and here I have x equal to L by x ref. So to make it 1, I can choose my x ref to be L. You could have choose your x ref to be 100 L. You could have choose, that is your choice. But then your x bar for the second boundary condition would be 1 by 100. Okay, but to simplify the things, we will say that our x bar here, sorry, x ref here will be L. Then that will be equal to 1 here. That is the x bar equal to 1 in the second boundary conditions. Okay. Okay, now if my x ref is equal to L, now already I have the correlation between my x ref and T ref. So if my x ref is equal to L, from this equation, okay, from this equation I can write my, okay, so let me write my x ref equal to L and my T ref then will be equal to x ref square by alpha, right? I think this was the equation, yes, and that will be equal to my L square by alpha. So I have already found my x ref and T ref, but I have not found my capital T ref, that is the reference temperature. Okay. So actually this boils down to what? This is now my L into x bar, that is okay. So you see, you have here theta equal to T by T ref, Ti by T ref, and here T2 by T ref, and here T1 by T ref. If you choose T ref equal to T1, then this will be 1, but this will be some another number, T2 by T1, and this will be some Ti by T1, some another constant. So what can be the best choice for T? Right? Now I define some other theta. So maybe I can call that as my theta tilde, and I define that as my T minus Ti by T2 minus T1. Okay. If I define it like this, then can I do something? Or let me write it as what? Sorry, let me write it as, okay, this is not a bad option here. One option is this, and I again define some theta star as my T minus T1 by T2 minus T1. Okay, I am just exploring different options for theta, the non-dimensionalized temperature. Okay, and I have not prepared anything. Okay, I have just uh, exploring the, I mean with you guys, I am also just exploring the various options. I have done these things long back in my first year of M.Tech. okay, in the conduction course. So after that, without any second practice, I am just doing these things. So any of these theta, either this theta or this theta tilde or this theta tripled, I mean theta star, anything you can use. So firstly, you just tell me, if you have to go from this t to this theta tilde, what thing will be there? I mean, what you have to do? That is, if I have del t del x, okay, you know that to go from x to x bar, I have to multiply x reference. But now if I have to go from t to theta tilde, then what I have to do? I have to just multiply this t2 minus t1, because you see now your t is what? Your t is theta tilde into t2 minus t1, right, plus ti. This is your t. So that means your del t del x bar is equal to del theta del x bar into t2 minus t1 into del ti by del x bar. Now this ti bar is a constant, and that is why this is equal to 0. So if there is any plus or minus in the numerator, okay, plus or minus of a constant, then that will not come during the non-dimensionalization. Okay. Similarly, if you have to go from t to theta star, then you have to multiply by only t2 minus t1, and this t1 will not have any effect. Clear? Okay. If that is clear, now you tell me that what will be these boundary conditions. Okay. So just let me copy this one for your sake. Okay. Copy, paste. Okay. So here you see, instead of t reference, if I have written my theta tilde here, then okay, so let me first work with theta star. So if I had written theta star here, then this will be, instead of t reference, this will be t2 minus t1, and this will be t1 minus t1, because this is my theta star. Okay, so let me write the theta star again. Theta star is t minus t1 by t2 minus t1. Okay, so this will be t1 minus t1, and now see that this is going to 0, this is going to be 0, and the second boundary condition will be at x bar equal to 1, because I have already assumed that my x reference is equal to L. That will be equal to t2 minus t1 by t2 minus t1 equal to 1, and my initial condition in terms of theta star will be, for any x bar into L, comma, tau equal to 0 is equal to my ti minus t1 by t2 minus t1. Okay, this is not any small number, I mean this can be any number, but at least we are able to turn down these numbers as 0 and 1. Okay, so these boundary conditions have been simplified greatly. Now if I explore the non-dimensionalized parameter theta tilde, so this time I will start by my initial condition, and that will be equal to ti minus ti by t2 minus t1. Okay, and this is 0. But now for my boundary condition, this is 0 and this is greater than 0, this will be equal to t2 minus ti by t2 minus t1. This is not equal to 0, any other number. Also for my another boundary condition, again, so this is t1 for the x bar equal to 0 case, and for x bar equal to 1 case it is t2. Again, this is not equal to 0 but some another number. So if I choose theta tilde at my non-dimensionalized temperature, then you see only my initial condition is becoming simple, but these are having some arbitrary constants. Those we don't know. Okay. Again, another, I will say you explore another thing, that is maybe theta prime, another non-dimensionalized variable, that is maybe t minus ti by t1 minus ti. You will find that here my initial condition will be, okay, so just let me write it, it will not take so much time, at any tau at equal to 0, sorry. Okay, so actually this is not the correct representation. So this I should have written the range of x here. I mean, the moment you write here x only, okay, from the start I will show this mistake. There is a small mistake in representation. I apologize for that, but I don't want you to take that mistake with you. Okay, the moment you write only x here, that is not a correct representation. You have to write for any x from L, from 0 to L, because you see x is varying from 0 to L. So if that is so, then this will be actually, you see here, this will be from 0 to L, and the moment you consider this x reference as L, this will turn to 0 to 1, because everything you can divide with L, right? Okay, so let me just write it. I have told you that I must write 0 to L, that is for all x. So that is equal to x reference into L, sorry, x bar into L, this one. So I can divide it by L, and this will be 1, right? That is the thing. Okay, so now you see, then this I should write theta dash for x bar for from 0 to 1 comma at tau equal to 0. So now you put here at this equation t equal to ti, that will be what? That will be 0. And now here theta dash at 0, sorry, theta dash at x bar equal to 0 and for tau greater than 0. Now you put here t equal to t1, okay, then this will be 1. But for the second boundary condition, this will be t2 minus ti by t1 minus ti. Okay, again you could have another choice of theta, this I will not show, this is maybe theta double prime, and that is equal to t minus ti by t2 minus ti. In that case, this boundary condition, there will be 1, and this you will have any arbitrary an arbitrary constant, that will be t1 minus ti by t2 minus ti, right? So you see, I am not able to, I mean, turn down all the constant into either 0 or 1, or in terms of any other integer, I mean simply any other integer. I can only turn down only 2 or maybe only 1 out of the 3 boundary conditions, and the, I mean out of the 2 boundary conditions and 1 initial conditions, right? So that is your choice, that, I mean, what non-dimensionalized temperature you will choose. So if, but mind it, if in the question paper itself it is given that you take theta as t by some t1, then you have to work with this only. You cannot change this definition of theta or the definition of any non-dimensionalized parameter if that is given in the question paper itself. If that is not given, then you can choose by your choice. Okay. So in this problem I will go with this one, that is this theta tilde maybe. So what, okay, uh, I will go with this one, this theta star. Okay. So let me just freshly write the non-dimensionalized problem. Okay. So the governing equation was, okay, so first let me write the non-dimensionalized. So this was x by L, and this theta was t minus t1 by t2 minus t1, and my tau is t by t ref, and t ref was L square by alpha. Okay. So that means here you see one very interesting thing, that means this L square by alpha must have the dimension of time, right? So if it is having the dimension of time, that means this alpha should have the dimension of L square by t. So I was telling that I don't recall the dimension or the unit of alpha. I can find the unit of alpha from this, that is alpha is equal to L square by t. Okay, that is meter square by second. Okay. So just let me confirm this alpha. It is x square. Okay, that is correct. So this is one lesson for you, that is, I think that you have already uh, come to the, I mean, this kind of non-dimensionalized things. And as far as I remember, this should be the chapter of lumped mass analysis, where in most of the books, just out of the blue, they define the non-dimensionalized parameters, but they don't tell the philosophy behind the selection of these non-dimensionalized parameters. Okay, because you could have argued that why L here, sorry, that is why L here, I could have written 20L, and why not 31L, and why here T1 and here T2 minus T1, why not 2T1, and why not 10T2, and here why not 100 T1 or any other temperature like 50 Kelvin or 250 Kelvin, why not? And here this is why not 10 L square by alpha, or why not 10 seconds or 20 seconds or 99 seconds. Okay, this is the answer, that why you should choose these things. And this sentence is also not correct, that is, you should not, I mean, there is no compulsion that you have to choose L here, you have to choose your theta like that, you have to choose your tau like that. You are the master of your non-dimensionalized parameters if, only if, I am stressing on this word if, the non-dimensionalized parameters are not given in the question paper. Okay. So now my governing equation becomes what? Del 2 theta. Okay, so I was, no, this is my theta, that is okay. This is equal to del theta del tau, and my boundary conditions were my theta at x bar equal to 0 at any tau for tau greater than 0 is equal to 0, my theta x bar equal to 1, my tau greater than 0 is equal to 1. This one is not looking like 1, and my initial condition is my theta at x bar 1 0 and my tau at equal to 0, that is equal to my Ti minus T1 by T2 minus T1. Okay, so this is my representation of the non-dimensionalized problem. I think this lecture is a bit heavy for some of you, those who have not thought about this thing earlier, that is why the non-dimensionalized parameters should be like this. So I would like to stop this lecture here, and also the camera is not working, that is why I have already stopped that. So from the next lecture I will be solving this equation, this non-dimensionalized equation, and after that we will take some other important problem. Okay, so just get yourself acquainted